Okay, chapter 21.5, electrical power. In the last chapter, we know that current, we know that the voltage, we know that the resistance, and also the combination of the resistor. Now, we will start the other one, is the power. This power, we know it before in mechanics, exactly the same. Related to what? Related to the energy output. Okay, power by the definition is the energy output over the time taken, or energy consumed over the time taken. And the unit of it will be watts, or 1 joule per second. Now look at the experiment of it. In this experiment, we want to focus on the power of a light bulb. How to do it? Of course, you should link up all the apparatus together. We call the starting reading. We will use the joule meter. In heat, you should know that what's the joule meter to measure the joule, the number of joule per unit time. Here, switch on the light bulb and then record the PD using the voltmeter and also using the ammeter to measure the current. And then switch off the power supply, we call the final reading, and then calculate it. This one is the initial energy, this one is the final energy over a specific time. Then after this calculation, you can find out the power. How is the brightness of the bulb related to the power of the light bulb? Once again, what's the definition of power? Should be energy over time. If you can see that the light bulb, the brightness of it is brighter than before, it means that more energy will be consumed. Then it means that the power should be greater than before. It means that increased. And second question, compare the power obtained P with the product of IV. After the experiment, you can find that power actually is similar to IV. Okay, but why? We will derive it later. Question number 3. Only a small portion of the electrical power is transferred into light. Where does the rest go? Of course, heat. Okay, next experiment. This one is a heating effect. Because the last experiment, we know that other than the light coming from the light bulb, we also have the heat coming from the light bulb. So here we want to study the heating effect of the electric current passed through a conductor. Procedure. We have the nickel wire. It means that this one is a material that it has higher boiling point or melting point. Okay, very difficult to melt it down even we have large amount of current or energy to give it to it. And this one connected to a cell, and then switch it on, and then observe what will happen for the rest. Here for the rest, the melting point will be so low, give it a certain amount of energy, it will melt down. And repeat the experiment using different wire, longer wire, like that, to change its resistance. Now what happened? How does the applied voltage affect the heating effect? After this experiment, you can see that the heating effect increases with the applied voltage. It means that higher voltage, heating effect will be higher. It means that more power will be given into it. For a constant applied voltage, how about the wire resistance affect the heating effect? Heating effect decreases with wire resistance. It means that if resistance is higher, then what will happen? Then the heating effect will be decreased. And the third one, how does the heating effect depends on the current? Okay, increases with current. More current, more charge passed through it, more energy consumed. Try to watch the video clip.
Glowing light. In our daily life, Many electrical appliances make use of the heating effect of current. We can demonstrate the heating effect of current using easily obtainable materials. Here is a pencil. Take the pencil lead out. Then connect the pencil lead to a DC power supply using crocodile clips. Use a clamp meter to measure the current through the pencil lead. Slowly increase the output voltage of the power supply. Whoa! The pencil lead is glowing!
Okay, in this experiment, you can find that the current passes through the lead, here, then it will give out energy. Okay, because you can see the light coming from it and also the heat coming from it. Then what happened? This one, we have this definition of the power will be energy over time. But can we add one more term into it is Q? Because when we add Q, you can see that Q over T should be the definition of current. Q over E over Q will be the definition of the voltage. Then using this method, you can find that out this one, IV or I epsilon. This one will be the power equation for the electricity. Okay, we know that the current, we know that the voltage are caused. Then this one we will know that the power consumed or power supply per unit charge. Now look at this. If we have a loading, usually the loading we will say that maybe the resistance R. Then based on the last equation, P is IV. What is V? V is IR. So we can combine it together, I square R. Or we change it. What's I? Will be V over R. Then this one will be V square over R. What's going on in this? It means that for the power equation, we have three different forms. We have IV without R. We have I square R without V. And V square over R without I. Depends on the situation. We can use one of them. Conservation of energy. It means that the total input power and total output power should be the same or less. The output should be less than input because we may have the power loss. And also for a network of loads, the total power output should be add them together because all the power should be a scalar without any direction. You just add them together. Look at this. Example 11. Okay, electric torch. Here we have the current, we have the voltage. What is the power? Very simple. Apply the formula. P is IV. Multiply them together. The unit should be watts. How about B? Electrical energy. Once again, what's the definition of power? Will be energy over time. The time should be 5.5 minutes converted into second. Then multiply them together. This one. Okay, example 12. Brightness of the filament light bulb, 鎢絲燈膽. Here we have three different circuits, three different ways. Sort the bulbs according to their brightness. The brightness, it means that more light will come out, more energy into it. It means that more power consumed by it. Now, what should we do? Here we have A, B, C, D, E. All of them will be identical light bulb. Once again, what's the power equation? If you know that I, V, then that's all. Of course, if you know that R, that's all. We have three different forms. Now in this case, which form should be used? Here, consider the voltage across each light bulb. Okay, and then you can see that light bulb A, D, E are all equal to epsilon. Okay, what's the meaning? It means that here, negative terminal 0 volt, positive terminal epsilon volt. So A, the PD across it should be epsilon. For third one, this one, should be epsilon, epsilon. This one is 0, 0. So D and E should be epsilon. But how about BC? For B and C, they are connected in series, division of voltage. Then it means that for B, only epsilon over 2. C, also epsilon over 2 only. Okay? Then apply the formula. You can see that in it, all of them should be equal to epsilon. And also the power equation, we have this. V squared over R is the power. And then try to look at here. All of them, the potential difference across it should be epsilon. What is the resistance between it? Here is R. How about this? Between it is R. So R should be R. Like that. Then after the calculation, this one is P. This one shows us that A, D, and E, they have the same power, same brightness. How about BC? They are identical, share voltage equally. So the PD across it only epsilon over 2. After the calculation, only this. It means that this one is the brightness of A, power consumed of light bulb A. For B and C, only a quarter of it. So using this, you can see that the brightness ADE should be the same and BC are the same but less than ADE. Okay, this one. Brightness depends on power. We know that. For the series circuit, the ratio of the power should be using this one. I square R. I square R. Here. Okay. But why? Because we want to use the common current to cancel I. Then you can see that R. It means that in the series circuit, more resistance than the more power consumed. But on the other hand, for the parallel circuit, we will use the common voltage. We will use different form, V squared over R. Then this one will be depends on the resistance. Greater in R, it means that the overall will be less. Okay. Part B, short circuit. I think all of you should know it in lower form or in primary school. Short circuit 短路. What is the meaning? It means that the current bypass a device. Okay. Okay. So look at this. Here, low current passes through the light bulb. These two cases. Originally we have the light bulb like that, but if you add one line here, bypass the light bulb cannot roll. Or you can bypass it like this. The current will not flow through light bulb and this. All the current will pass through this. Okay, then all of them we will say that short circuit. Okay, if this one, if I bypass the light bulb like that, then what will happen? You can see that this connected wire will go through the whole circuit without any loading. It means that R will be very small. V is IR, but R tends to 0. Then I should be very large because V is constant. Then current will be very large. This one will have great heating effect, large enough to melt down the wire, the copper wire, to catch fire. Okay, Ch21.5. Here, electrical power can be calculated using this four formula below that. For each, this one, state the physical meaning of the symbol. Very easy. P means the power, V is the voltage, PD across the load, I is the current flow through the load. How about this? The one difference is the epsilon, EMF of the source. and also the power will be dissipated by the load, current through the load. How about this? I square R. Similarly, this one, this. You can stop the video and then copy it. How about this? Under what circumstances is it applicable or useful? It means that this formula we can apply it, but in which situation? Here, PD across the load and the current flow through it is known. It means that we know that the current through the load, we know that the voltage across the load, then we can apply this formula. For this, we know that the EMF and also the current flow through the battery or the power supply. For this, we know that the current pass through and also the resistance of the load. For this, we know that the PD across the load and also the resistance of the load. Question number 2, the third equation. P is proportional to R, but the fourth one is inverse of R. Then it seems to be contradiction. Mathematically, this one is correct. R increase for the first one, this one, P should be increased. But for this, R increase, P should be smaller. Then how to explain it? This one in examination, common examination, is a common question. Look at this. These two equations are actually using in different situations. For P is I square R. This one, we assume that I is constant. For the second one, P should be V square over R. V is a constant. So, seems to be contradiction, but it's not. Depends on the situation. Different situation, we will apply different formula. Actually, they are the same. The third one, we have 3 light bulb A, B, C, different ohm, and find the power of it if they are connected in series. Once again, for connected in series, they will have the common current. Current will be the common factor of them. Then it means that in order to find out the power, you should use I square R, and then you get I. Then it means that greater in resistance, more power. Okay, or you can use this complicated example to find out the total current. Should be 12, because for the total potential difference, the total equivalent resistance should be 2 plus 4 plus 6. After calculation should be 1A. 1A will be the common current, and then apply the formula I square R. Then you can see that the ratio should be 2 to 4 to 6. The total power should be 2 plus 4 plus 6, 12. Okay? Or, for the total power, you can find out the total resistance should be 12. Total resistance is 12, using I square R. I square R is the total power. Exactly the same. If they are connected in parallel, then what will happen? Because the parallel circuit, all of them will have the same voltage, but different in R. So for PA, 72, 36, and 24, final power should be this. Or you can find out the total resistance for parallel circuit, add them together, should be RO equivalent. Okay, you can pair your calculator and then find out the total resistance. And then if you know that the total resistance and also you know that the voltage, then you can use the total power should be V square over R. Okay, then you can put it in it. This one should be 12, and this one is 1 over R. It means that this, okay, this one, the common factor should be 12. This one is 6, this one is 3, this one is 2. So after the calculation, you can find that 12, cancel one of them, and then this one is 11. 11 times 12 should be 132. Okay, you can find out the total resistance or equivalent resistance first. Last question. No, not last one. Okay. Question number 4. What happens if bulb A and bulb B is short? Okay, if these two are shorted, it means that maybe this and this or this. Then what will happen? A shorter one grow out. If you short it like this, A will not grow, only B will grow. Okay. But if both of them are short, then all light bulbs goes out and the wire are heating up because here we have large current pass through it. Question number 5. Why a shorter battery go flat quickly? Go flat means that without any energy at all. Here, because the energy stored in the battery is limited, as the power dissipated become very large, because large current, okay, very large current to give out amount of energy in a short time, then the time span of it will be shortened.